Hello and welcome to this HydroComp webinar about PropElements 2017. My name is Don McPherson. I am the technical director here at HydroComp and I will be your host for the webinar today. Just a few initial notes before we begin. You should see a chat bar on the left side of your screen. Please use this to send any questions, and we'll try to answer these questions during the course of the webinar or at the end. Let me ask right now for a quick audio check from the participants that sound levels are acceptable and you can hear me okay. Please send a quick confirmation of this through the chat window if you would, please. And finally, before we begin, this is a brief introductory webinar about our new prop elements, so we encourage you to reach out to us later for additional information. Looks like sound is fine, so we will get right to it. PropElements 2017 is HydroComp's newest software product. It is what we call a propeller designed for performance code. A number of you will be familiar with some of our other tools, NavCad, for example, and PropCad, which is a design for manufactured geometry modeling code. So PropElements is our analysis and design tool that offers an intermediate level of propeller detail. We'll see here a little later on where it sits in the propeller design and analysis process between tools like NavCad, for example, which uses parametric methods to describe and calculate propeller performance, and a full three-dimensional CFD, for example. PropElements also is what's called a wake-adapted code, so it considers the influence of a vessel type or even a specific vessel. And that's an important concept to carry through here, is PropElements can be used to represent semi-custom type vessel, vessel-specific or vessel type applications. So before we go into the nature of PropElements, its capabilities, its interface, and how you use the tool, I wanted to lay down a little background about propeller performance calculations in the scope of the order of the calculation, starting with the most fundamental and going to the most complex. Empirical or statistical series. Many of you will be familiar with the B series, for example, and there's a graphic at the bottom of the screen that shows the blade outlines, foil shapes, and pitch distribution for the standard 4-blade B series propeller. Now, this is characterized often as a 1D calculation, where the geometry is based on a parent propeller, and that propeller has a single pitch that represents its entire pitch distribution. It also has a single blade area ratio that represents its outline shape, and that propeller is changed in a systematic way, modified with a different pitch over diameter ratio, different blade area ratios, but they all start with a single parent. The inflow to this propeller is by a representation of a wake fraction. It's a single averaged axial velocity over the entire propeller disk. There's no distribution or wake field, if you will, described in wake fraction. Now, the method that's used for empirical statistical 1D performance calculations are polynomial equations. Many of you will be familiar with this. If you're a graduate naval architect, you will have seen these equations developed from charts in school. And these are the equations that are used in our NavCad software and PropExpert and Swiftcraft, for example. Now, the design capability or the scope of design for this kind of calculation will be limited to sizing or matching proper diameter, pitch, blade area. for example. And this is very important because these are the tools that are typically used for system level calculations. It's always better to find the optimum system before trying to optimize components, such as the propeller itself. So the hull, propeller, driveline, transmission, engine system can be optimized very efficiently and matched appropriately between the propeller, the transmission, and the engine, for example. And NavCad, of course, is the principal tool that is used for these kinds of calculations. Now, here's where we enter the domain of prop elements. It falls under what's called a blade element code, also characterized as a 2D calculation, where the geometry is by a parent foil at the different slices. As you can see from the graphic there, we have a light gray slice through there, and you get a thrust and a torque, from the foil lift and drag. So this allows you to have a greater definition of the propeller by radially defining pitch, camber, thickness, chord. You can kind of think of it as the foil's bounding box. Now, inflow is not just a single value, such as wake fraction, but you can use radial variations in axial and tangential or rotational velocities. The addition of the tangential velocities is another increase in order above a simple wake fraction. Now, the method of this is an integration from the root to the tip of what we call scalable slices. Each of these slices has a foil shape to it, and there's a calculation of lift and drag, and those are integrated. Now, that's a very simple overview of the methodology. We can talk in detail about it later. And the design we have is now component design, where we have automatic or analytically optimized pitch and camber distributions, but we also have strength and cavitation checks for blade thickness and chord length. So all of the radial definitions of pitch, camber, thickness, and chord can be optimized and designed with prop elements. Just for perspective, at the highest end, we have full geometry flow codes. These are described by panelized 3D surfaces. The image that you see here is a graphic extracted from a CFD calculation of a ducted propeller. It's a propeller through, it's a Kaplan propeller through a 19A nozzle. You can see flow lines, but each of the components, the nozzle, the propeller, the hub, even shafting upstream, needs to be modeled by panelized 3D surfaces. The inflow, of course, is the full wake field. It's whatever is in front of the propeller will be modeled as it goes through the propeller. Methodologies, I'm not going to go into the details of that. There are various types of CFD calculation codes. RANS is a popular one, Reynolds averaged, Navier-Stokes. And the design using CFD is that it is typically coupled with some kind of an external optimizer. CFD arguably can be described as an analysis tool. So the design, which requires investigation of different options through analysis, typically looks to an external optimizer to solve for some kind of an objective, whether that be highest propeller efficiency or least noise or whatever the design objective is. And just to kind of summarize the three and where prop element sits in this, the empirical-statistical series, the lowest order, it's anchored to a series geometry, B series gone. It is robust and very, very fast, of course. Now, blade element codes, prop elements, we can extend the kinds of performance prediction into the prediction of velocities and volumetric flow rates. We have a greater variation in the geometry that we can model. It's still very cost effective and still accessible to any user. Full geometry flow codes, CFD, extensive performance prediction. It's absolutely critical in when you need to observe flow. Neither of the other two levels are able to observe flow, and neither of the other two levels allow for completely unconstrained and arbitrary geometry. This does come at a cost, however. It has a high computational demand, and it requires a level of user knowledge of the methods that's not necessary for empirical or blade element codes. Now, the principal tasks of PropElements, and I'm going to introduce just this here before we actually begin to run a sample calculation for you, is there are three principal page groups. We have a propeller page, which defines our geometry, the radial definitions. We have a performance page, which is where our design and analysis is conducted. And we have a strength page, where we can calculate stress, safety factors, and body forces. We have a variety of supplemental tools that are useful. One is the generation of KT, KQ, and KTN for nozzle curves. There's geometry smoothing and manipulation of the shapes for the user experience of a design. There's also a variety of export options to make PropElements a tool that can work in conjunction with other tools, such as our PropCAD software for geometry definition, for example, and also NavCad, where the performance curves, the KT-KQ curves, can be used as part of a NavCad calculation. So let's take a quick look at PropElements here. This is the interface of PropElements. It's a Windows program, of course. And just to put this into perspective, I'm going to run this real time. This is a Windows 10 computer that I'm using, just a fairly generic business laptop. I've made the screen a slightly lower resolution, so it shows up a little larger on the webinar screens. But if you had a larger monitor, higher resolution screen, you would have more real estate for the program here. So let's take a look at what we have in front of us. The screen that you see is our propeller page. We have a project group here that gives the principal characteristics. It's 4 blades. It has a 3 meter or 3,000 millimeter diameter propeller. And it has characteristics about the configuration, the kind of propeller that we want to model. This is going to be an open propeller, but we can also do a variety of ducted propeller options, including 19A, 37 nozzle, 2 popular ones. The 33 and 34 are decelerating nozzles. We can even put this into a circular tunnel, such as a bow thruster, or we can look at a representation of a high efficiency nozzle. And we'll talk about these other details a little later. So we have a hub-driven. We can do rim-driven propulsors, a hub-driven open propeller, fairly standard, fairly typical propeller. This is a quick profile and outline representation of the data that has been entered. So let's step through our radial data here for a moment. We have our radial distribution non-dimensionalized, which is typical for propeller design from the root up to the tip. We have a chord length, thickness, camber, pitch, rake, which is 0 in this case, skew, and then variations of that, skew angle, and then we have distributions of skew angle. Sometimes these are important or interesting to look at. This column here, the leading edge skew angle, a derivative in the degrees per radial position, can be very helpful in identifying leading edge smoothness for hydroacoustic properties. And then we have an interaction or a blockage to make sure that the propellers are not getting in the way of each other. Then there are non-dimensional variants of these, such as thickness to chord ratio. So this information can be created in a variety of ways, but typically you have a fundamental shape that you want to start with, whether that be a B series or a Gone style propeller, a Kaplan, whatever it may be. There's a summary calculation that gives the mean pitch. In this case, all pitch values are 2,900 millimeters, expanded area ratio, blade thickness fraction, and calculation of the total skew. So this is a very good overview of the geometry. Now, this view here, we've seen some of the graphics. This is also where we can create reports that can be exported as PDFs or exported to Excel, for example, as a CSV file if you want to do additional manipulation of the data. Now, the data entry, you can always paste and copy columns. We'll see that here in a little later. So we've looked at the geometry and the basic outline, and like all good engineers, we're going to save our data frequently. So we'll just save that right there. The next step typically is to run an analysis. So we go to our second page, our propeller page, or our performance page. So our analysis that we want to run is we're going to run this at 20 knots, and we're going to just simply scale that to a particular wake fraction. And I'm going to choose a value of 0.059. So when we enter that, what you'll see is that the column here on V axial has the 0.059 wake fraction considered. So this model will have a radial distribution that's constant at 18.82 knots, and we're not going to consider any rotational velocity at this point, because let's say we may not have any values for that. So we'll just assume everything is axial. Now we're going to run an analysis of this propeller at 250 RPM. So we're going to solve for thrust, and this reference torque and power fields allow us to enter in benchmarks. So I'm going to put 2,700 kilowatts as the value that I want to make sure I do not exceed. One of the pieces of the performance prediction, as I mentioned earlier, is the integration of thrust and torque, lift and drag. And we do that through a variety of different foil type options. We have a generic foil. For those of you who have a hydrodynamics background, this is a variant of the Prandtl-Schlichting drag prediction and basic foil lift algorithms. We can specifically create NACA 66 type designs, bicircular, which would be something for a tunnel thruster, for example, where you have symmetry both in thickness and in chord length, or you can create a custom drag coefficient for the foil if there's a particular reason to do so. Now, I won't go into the details of ideal angle, but this is a numerical way to quantify the type of the camber distribution that your foil might have. And we'll just use a standard calculation setting right now. We'll see how this is used a little bit later on. When we run a calculation, what it did is it iterated the calculation of the induced velocities that the propeller was developing and resolving all of the flow and angle vectors, and then calculating drag coefficients at each radial position, lift coefficients at each radial position. This is a a description of something that's called circulation. This is the radial blade loading. You can see most of the work is being done in the middle part of the blade span, as would be expected. Now, as I look at the columns here in the cavitation group, I see that there's a number of radii that have exceeded my minimum recommended chord length. This is an assessment of something called a cavitation bucket that determines how much chord length you need in order to ensure that your cavitation is kept below critical levels. This is a cavitation number, local cavitation number, and we also present a minimum recommended leading edge radius so that you can avoid flow separation. So these are design guides that you can use to help improve the shape and the characteristics of your propeller design. Once we have our design in place, this particular analysis, the calculation summary is presented here in this middle table, and we can just take a look at a couple things. Our blade efficiency is at 0.73. Very respectable number. Cavitation is only 5.2%. However, we are requiring more power than we have available, and that's why these fields are in red. User feedback will occur when fields change color to red, and in this particular case, you can see critical fields are represented in bold. Now that we have the analysis completed for our existing propeller, let's take a look at a strength calculation. What we're going to do is we're going to set this up with representative values for nickel, aluminum, bronze, but we can put in any number if we were doing a plastic propeller, and then a parent foil form. Now, it's important for me to make it clear that the shape of this foil is not used for the performance calculations. That's the selection of the foil type on the performance page. But when we're doing strength calculations, the section properties of the propeller are important. So we're looking at just a typical NACA 66. We have a NACA 16. We have a NACA 16 and NACA 66, and also custom options with an integrated editor. We see the neutral axis shown here in the dashed line, and we can, flip through our different radii and see what the different foil shapes are. Now I'll run my calculation, and then I can look at total stress values, safety factor distributions, and we can see what the minimum safety factors are and the maximum stress. So we have a 5.3 safety factor on yield and a 12.7 safety factor on our ultimate tensile stress. Now, one of the things that this tells us as a design guide is we may be carrying more thickness out in the outer radii than we need. So we could go back and reduce our thickness, change our thickness from a linear distribution, for example, to more of what's called a cantilever style distribution. These last three columns give us what's called body forces or force distribution. This is at each radii, it's point forces of the axial, tangential, and radial forces due to the circumferential mass-based tensions that are created. So these forces can be brought into finite element analysis, for example, to give a very good representation of what the load on your blades are going to be if you need to do a more detailed strength study. And as mentioned earlier, this is the screen where pages are shown either graphically or, in this particular example, in report form. So we have 3 pages that we created here, one for the propeller, one for performance, and one for strength. And we can print that directly, or we can export and save this as a PDF file, for example. Okay, so we've looked at the propeller page, the performance page, and the strength page. Let me take just a brief slide here to comment on calculation accuracy, because that's kind of the name of the game, is that we need not just to do this in an academic way. Our objective here is to help you develop geometries or analyze geometries that can be accurately modeled. And I just selected 3 representative propellers here. The first 2 are from US Navy skewed propeller series. This first KT-KQ plot, we have the KT-KQ efficiency is for a 0 skew. This has the same fundamental propeller, but at 36 degrees of skew. And you can see we're modeling both quite acceptably. And this is a ducted propeller model. I believe it's a 4-blade Kaplan with a 0.55 blade area in a 19A nozzle. But you can see we're picking up not only the propeller or the total KT, but our nozzle KT as well, and our propeller KQ for the torque and the total system efficiency. That's one of the real strengths of PropElements, is its ability to analytically wrap a nozzle or a shroud, whether that be a 19A or something like a tunnel thruster, around our propeller for our analysis and design. Okay, so given that brief introduction to the tool, why use PropElements? Well, we would use it in general if our propeller is non-series, such as if we were designing a NACA 66 foil-based blade versus a B series or a GON. If inflow is non-uniform, if a single wake fraction number does not do a good job at representing the calculations, or if the propulsor is not represented in a way for a parametric statistical analysis, if it's a rim drive propulsor, if it's a tunnel thruster, or even special kinds of nozzles. This graphic here to the lower right is a NACA 66 based propeller inside a high efficiency nozzle. So there's no way of exactly finding empirical data or a statistical method for this. That's where PropElements becomes particularly strong. We would use PropElements for analysis if the blade count or the width is outside the scope of the series. This image here on the aft end of a torpedo-shaped underwater submersible is a GON geometry, but the 2 blades and the very thin blades are outside the scope of the series. If nozzle effectiveness is compromised, we're going to talk about that a little bit later, or where you want to investigate propeller modifications, such as repitching or cutting back before action is taken and the expense of bringing in a propeller shop are spent, or if you need body forces for CFD or FEA calculations. We would use PropElements for design if we want to create high-value customized propellers beyond just the scope of the conventional systematic series propellers. If we want to do things like unloading a tip for hydroacoustic considerations, and we'll see that here in just a minute. If we want to export KT-KQ curves for a variety of reasons, or if we want to compare induced velocities for things like industrial mixers or calculation of induced volumetric flow rates, which can be used in studies of rudder effectiveness, for example. A very valuable purpose for CFD that we're seeing more and more is its use as a preparatory step for CFD. PropElements can conduct a variety of preliminary design space investigations to get you closer to the answer or refine the design before launching CFD with its corollary expense, time, and resources. But one other important aspect is that the quantitative strength of PropElements allows it to establish benchmarks such as thrusts and torques, or even velocities and volumetric flow rates that you can then use for CFD model validation if your CFD model is substantially different than the outcomes that you're getting from PropElements. You might begin to ask why. Is it something about the gridding? Is it something about the turbulence selection? You don't know why there's a difference, but at least it provides some confidence that your model is of appropriate fidelity. Who should use PropElements? Obviously, propeller designers or consultants currently use PropElements for creating optimized custom designs, or semi-custom product models. You can create something that is not unique to a particular vessel. It's unique to a vessel type. What I mean by that is we can represent the inflow in the wake field by a particular radial wake distribution that's not specific to a particular motor yacht, but is representative of the family of twin screw motor yachts. Of course, the design of integrated propeller nozzle thrusters, or because PropElements allows for the calculation and use of variation of inflow and discharge velocities, this can be used for multi-blade element designs such as contra-rotating, stator, propeller designs, or even rim-driven designs. The image here was a project that we did last year for a company here in Portsmouth, New Hampshire. This was a contra-rotating bow propeller, a tractor style propeller that was designed with PropElements. We see greater use of PropElements for and by naval architects to evaluate contemporary product models. You are not necessarily responsible for the delivery of the final propeller, but you are responsible for the success of the system. And that system, the hull, propulsor, driveline, engine system, does include the propeller. You want to make sure that it's not overloaded, that it indeed has the ability of delivering the performance that is claimed. So you can extend that to validate alternative propeller proposals, investigate what gives you higher efficiencies, lower cavitation, for example. You can use it to develop data for torsional analysis or KT-KQ curves. Hydroacoustics, noise and vibration, is becoming a large design driver, and we have in the works some fundamental hydroacoustic models to include in the performance page, so you can get a quick metric that you can then compare things with. And finally, to assess risk for component uncertainty. And by that, I'd like to just use an illustration of a project that we used PropElements on for a ducted propeller that was not meeting its bollard pull requirements. The image to the left is a ducted propeller. As I said, is a 19A nozzle with a Kaplan blade form in it. And what we're seeing here is a CFD image without any hull in front of it. So we can go back to the empirical models to find out how well our calibration is. But I want you to look at the flow lines, these dark contour lines. What we're seeing at a bollard condition is that flow comes from the side in. An important part of nozzle thrust making at Ballard is this curvature of flow. Without the curvature of flow, the nozzle can't create its lift. Well, what we saw through the CFD modeling was that flanking rudders in a close proximity ahead of the nozzle was not allowing this good curvature of flow around the annular part of the nozzle. Right across the flanking rudders itself, they were running flow lines horizontally. So the nozzle was losing its effectiveness, and that effectiveness changed the inflow to the propeller and subsequently its thrust and torque. So while we cannot model the flow characteristics like this in PropElements, this is something that you would require CFD for. What we can model is nozzle effectiveness. We have the ability in PropElements to choose a nozzle type, 19A for example, and derate the effectiveness of the nozzle and begin to observe what the changes in thrust and torque are going to be. So if you have a head box on a nozzle that's eliminating some of the flow around the nozzle, or you're considering appendages or upstream devices that may be affecting the flow, you can use PropElements to assess the potential cost or risk of some of these upstream components and decisions. We had a quick question here on pre-swirl stators and contra-rotating propellers. So let me just step back here. We use PropElements currently for multi-blade elements where we will actually run two projects side by side. We'll have a PropElements project up for the forward blade set and one up for the after blade set. And I use an Excel spreadsheet to handle the interaction of the velocities. So it's a kind of quasi-manual optimization that we let PropElements optimize each of the blade sets for the inflow characteristics, but we allow those inflow characteristics to iteratively change using this external spreadsheet. We have in our design notes and schedule that we hope to be able to get to an integrated blade element design where you would have a stator page and a propeller page, or a forward propeller and after propeller page for contra-rotating propellers. But that's going to be a good year out, I suspect, before that's ready for release. So we'll come back to that a little bit later. What I'd like to do is now to extend this into a little more customization, where we want to modify some of the radial geometry and do some things with the propeller design side. Now, if you'll recall, we had a number of chord lengths that were too short. So what I'm going to do is I'm going to copy these, and I'm going to bring this back to the corresponding spot in the chord length. You can see how those chord lengths increased. Well, this is a very unfair shape. So what I'm going to do is I'm going to first take this 0.6 and I'm going to fit that point. So I'm going to go down to my 0.6 column here, and I'm going to fit this point. So I'll accept that fairing. It's still not great. It's a little bit better. So I'm going to use a mathematical fairing on this. We have a couple different spline types or algorithm type. One is a normal, but because our chord length goes to 0 at the tip, I'm going to use a tip weighted, and I'm going to loop through different levels. That's not bad. I can get a little bit closer, or I can do a very tight smoothing. So I'll accept that. So now I have a chord length that has the increase in the blade area and the increase in the chord lengths for cavitation specific objectives. So what I'll go in here is, now what I want to do is I'm going to vary my wake distribution. So I'm going to scale a wake distribution. Well, I haven't entered a wake value yet, so that's what this warning is. I'm going to go into and import a representative twin screw wake field. So this is the radial distribution of velocities. And if I just choose that value, that would be 0.066. But I want to scale that to 0.059 to be the same as I had before. So my mean velocities are going to be the same. But now you can see I have a variation in my axial velocities for the propeller. This is similar to what would be done in a multi-blade element design, where we would be taking the output of the forward blade and entering it in as the input for the after blade, with appropriate corrections for axial distance. Getting back to this, what I want to do now is I want to size or solve for pitch. I want to design a pitch, still for 250 RPM, but I want to do it for 200 kilonewtons of thrust. And we still have a 2700 kilowatt constraint on that. Now, one of the other things that I want to do is I'll want to perhaps consider blade unloading. So I'm going to unload my tip with what I call half unloading here. And I'm going to distribute that from the 0.6 radius out. So here's the recipe, if you will, for my new sizing, my new design. Oops. Let me turn on interactive here. What this does is it allows for integrated smoothing of the pitch distribution. The reality is, mathematics of these kinds of calculations sometimes lead to quasi-singularities, particularly at the tip, and we may want to fare some of those things out. So I'm going to do a smoothing of my pitch, a recalculation. And so now I've shifted my loading away from the tip. Let me bring this back to standard, and I'll show you what the difference is. Look at my blade loading here as it changes. Once it's designed, I have more blade loading towards the tip, less blade loading towards the midspan and into the root. So I can control how much of the blade or how much unloading the tip needs if I'm designing for hydroacoustic properties, for example. And let's take a look at the cost of that. I went from an efficiency of about 0.727, 0.73 now to 0.72. But I have my loading shifted away. And if we look now at our cavitation, we see that our blade chord lengths are all acceptable now. A quick check of my strength. You see the safety factor went up a little bit. That's because the beam, that's the blade, had its loading shifted from the outer radii more towards the inner radii. So we have a tremendous amount of control for design and analysis. For analysis, we can solve for thrust. for design, we can solve for a pitch distribution. Or if we want to really optimize for a particular operating scenario, we can optimize and design for pitch and camber. So just as a review, PropElements 2017 is a tool used for non-standard propellers. Series propellers, a true B series, a true GON, are well represented by the statistical empirical methods. It allows for analysis of existing geometry, but we can also do design of optimized wake-adapted propellers. It supports open and ducted propulsors with standard nozzles, non-standard, and even tunnels, hub-driven or rim-driven. It gives you a strength assessment and a preparation of the KT-KQ curves. With that, let me say thank you for your time here today, and we'll get into some questions here in just a moment. But you can find more information, of course, at hydrocompinc.com. Certainly reach out to me at my email address there if you have any questions. And our next webinar will be April 5th, which is a prop expert for powerboats. But let me open the chat room to anybody that has some additional questions, things that I can dig a little bit deeper into or clarify. Okay, let me comment on a question about duoprop. The duoprop as a Volvo Penta product model would not be something that we could do with complete confidence in PropElements, and let me tell you why. At this point, the lift and drag calculations and the performance are subcavitating. We can represent the expectations of cavitation, but right now there's no correction for performance change if we get into very high thrust loading. Duoprop is an outboard style small propeller, often runs in a mode that would be well modeled by PropElements. But I just want to make it clear that if you get into very, very high blade thrust loading, you might exceed the scope of PropElements in its version right now. We do have R&D in place for extending the scope of this to additional cavitation breakdown, and for things like localized camber and the like. We have a question about smoothing of the chord that we did. Will it automatically adjust chord length to meet cavitation criteria? And can you select various cavitation criteria? The cavitation criteria that's used for the chord length here is based on the fundamental cavitation bucket, where you've got three different kinds of cavitation being considered. You've got a bubble cavitation and you've got sheet cavitation, and these are typically found at the nose and on the suction side and on the pressure side. So you have a variation in angle of attack that looks at these, and the chord length representation that we have here really is not based on the traditional cavitation criteria that you might consider for a system level, like 5% cavitation or sigma tau charts and some of those things, or blade pressures, because that's a whole propeller blade metric. What we're trying to do here is to provide a cavitation criteria on a radius by radius level, and that's why we use that kind of a specific a criteria as opposed to a generalized criteria. Now, does the question about automatically sizing the chord length? No, we don't do that for a couple reasons, not the least of which is we don't want to take the engineer out of the loop at this. I'd like you to look at the chord length at the root here. This is the minimum chord length from the cavitation requirements. If we look back here at what the chord length was that we originally entered, this chord length is as much about strength as it is about cavitation. And so if you were to reduce the chord length for an appropriate strength, you'd be increasing thickness. And so you really don't want to have a tool automatically take this minimum chord length column and use this as the design chord length for the next iteration. We want the user to look at this and know that I have considerations of strength and thickness and manufacturability and a variety of things that the program just simply can't know. Mentioned formal optimization. Great question. Could we run PropElements in batch mode similar to what we do in NavCad Premium? For those of you who don't know the context or the background of the question, NavCad Premium and the Premium edition of PropElements has what we call a scripting capability. And scripting allows these tools to be run with a command set as opposed to the interface. Well, once we have that ability, we can then begin to communicate with third-party software, such as Excel or a program from our friends in Potsdam, Germany called Casis that can communicate, package the data that NavCad or PropElements would need, shell the program, run it in a silent mode, return the output back to the administrator executive program that asked for it. And so you can do a variety of external optimization scenarios. And in fact, this is how I will be doing multi-blade element work in the future, is by having Excel, instead of doing this manually, transferring the data back and forth, I would be doing this automatically by allowing Excel or MATLAB or any other tool that you want to use that has a similar kind of a batch mode capability to handle that before. And certainly we would do that in our development work, prototyping. But the short answer is yes, we can run PropElements in that batch mode scenario from a program like Excel or Casis. Excellent. As I see no more questions at the moment, again, let me thank you all for taking the time today with us, and I hope we wet your whistle a little bit on what PropElements can do, and what we would certainly love is to hear from you with any detailed questions, applications you'd like to consider, or arrange for a private demonstration of PropElements with some of your own sample data. With that, let me say thank you again. Have a great day, and we look forward to seeing you at our next HydroComp webinar.